You know, we all had to learn the rules of exponents back in school. We crammed them for tests, but did we ever really get them? In this explainer, we're going to throw out the old rulebook and actually build some real intuition from scratch. And we're going to kick things off with this amazing question from Reddit. It seems so simple, doesn't it? But as this user found out, this is the kind of question that can trip up even people with PhDs in math. So why is that? Well, it's because the answer isn't just some rule you memorize, it's a story. So section 1, the zero power mystery. Our whole journey starts right here with this idea that the answer isn't something to be memorized, but a conclusion we can actually figure out for ourselves. Okay, next up, back to first principles. Yeah, to solve this big mystery, we have to go all the way back to the beginning, to the most basic definition of what an exponent even is. And really, that's it. At its heart, this is all an exponent is. It's just a little bit of notation that mathematicians came up with to save themselves from writing out these super long strings of multiplication. The big number on the bottom, that's your base. And that tiny number up top, the exponent, that's just a counter. So here's what that looks like in the wild. When we see x to the power of 3, all it really means is multiply x by itself 3 times. And honestly, if you get this one idea, you've got the key to unlocking everything else. All right, section 3, building the rules. Now, let's see how the rules of exponents aren't just random. They're actually logical consequences of this whole repeated multiplication idea. Okay, let's play with a simple problem. What happens when you multiply two exponential terms that have the same base, like x squared times x cubed? Now, let's not jump to a rule. Let's just think about what this actually means, based on that first principle we just talked about. So if we just write it all out, well, x squared is just x times x, and x cubed is x times x times x. So when you multiply them together, what do you get? You just get 5 x's all multiplied together, which we can write as x to the power of 5. And just like that, we've basically discovered the product rule. The shortcut is to just add the exponents. See? It's not some weird magic rule you have to memorize. It's just a faster way of counting up all the x's. Okay, so that's multiplication. What about division? Let's try x to the 5th divided by x to the 3rd. And again, let's forget the rules for a second and just expand it out to see what's really going on. So if you picture this as a fraction, you got 5 x's on top and 3 x's on the bottom. Now, we know any number divided by itself is just 1, right? So we can start canceling out the pairs. And what are we left with? Just 2 x's on top. In other words, x squared. And boom, there it is. We've just figured out the quotient rule. The logical shortcut is just to subtract the bottom exponent from the top one. It makes total sense. We're just removing those canceled terms from our count. Okay, this is it. This is the moment we've been building up to. We've just built 2 totally logical rules from one single simple idea. And with these tools, we are finally ready to crack that zero power mystery. Okay, let's walk through this together step by step. Let's think about x cubed divided by x cubed. On one hand, from basic math, we know that any number divided by itself is always 1, period. But on the other hand, let's look at it using our brand new quotient rule that we just discovered. We subtract the exponents. 3 minus 3 is 0, so we get x to the power of 0. So you see, since both of these things have to be true at the same time, the conclusion is absolutely inescapable. X to the power of 0 must be equal to 1. It's not a rule we memorize, it's a result we can actually prove. Okay, section 4, negative and fractional powers. So now that we've cracked the big mystery, we can actually use that same logic to explore some even weirder stuff. Check out this pattern with powers of 10. 10 cubed is 1,000. 10 squared is 100. 10 to the power of 1 is just 10. Notice what's happening. Every single time we decrease the exponent by 1, what are we doing to the final number? We're dividing it by 10. So, following that exact same logic, if we go from an exponent of 1 down to 0, what logically has to come next? We just divide by 10 again. And 10 divided by 10 is 1, which perfectly confirms what we just figured out. But why stop there? Let's keep the pattern going. What's 1 divided by 10? It's 1/10, or 10 to the negative 1. And if we divide by 10 again, we get 1/100th, or 10 to the negative 2. So you see, a negative exponent isn't some strange new rule. It's just a continuation of the same division pattern, and it creates reciprocals.
Fractional exponents also make perfect sense if we use our rules. Think about it. What's x to the 1/2 times x to the 1/2? Well, if we use our product rule, we just add the exponents. 1/2 plus 1/2 is 1. So x to the 1/2 is the number that when you multiply it by itself gives you x. And what do we call that? That's the definition of a square root. The denominator of the fraction is simply the root you're taking. Okay, section 5. Let's talk about some of the most common pitfalls and use our new intuition to see why they happen and how to avoid them.
Ooh, this is a classic one. People always forget the coefficient. That exponent on the outside of the parentheses, it applies to everything inside. It's easy to remember to multiply the exponents for the variable, but so many people forget that the power also applies to the 2 out front, so you have to calculate both 2 to the 5th and x to the 3 times 5.
This might be the single most common mistake in all of algebra. Seriously, it just feels so tempting to distribute that little power inside, but it completely breaks our first principle. Remember, the exponent means multiply the entire base by itself. And in this case, the base is the whole thing, a plus b. So we have to multiply a plus b by a plus b, which gives us that correct, longer answer.
All right, final section, putting it all together. So why is it so important to get these fundamentals right?
Because when you truly get these rules, you can look at something that seems totally terrifying and overwhelming like this, and you know that you can tackle it. Step by logical step, you can simplify it into something you can actually manage. Every complex problem is really just a bunch of simple steps built on the foundation we've just covered.
At the end of the day, understanding the why behind a rule is so much more powerful than just memorizing it. These principles are really the language of growth and scale, and they're used in everything from calculating compound interest to understanding radioactive decay. It really makes you wonder, what other simple math rules out there are holding a whole universe of complexity?